Thank you, Alex. Good afternoon, everyone. As Alex said, my name is Stephen Chan. I'm from Monash University here in Australia, but I'm here as the president of the Scientific Committee on Antarctic Research, or SCAR, principally for two reasons. Chief amongst these is that we're here to announce the ninth winner of the Tinker-Muse Prize for Science and Policy in Antarctica, although, of course, it's no secret since it's on both panels on either side of me. SCAR administers this prize on behalf of the Tinker Foundation, and I'd like to just mention a few words about the foundation since they've been supporting this extremely significant prize for the last decade. The mission of the Tinker Foundation is to promote the development of an equitable, sustainable, and productive society in Latin America, and to enhance understanding in the United States of America of Latin American problems and how US policies may actually affect the South American region, or the Latin American region. Of course, this is a little different to what the prize is about, and the Tinker Foundation, in recognizing the interest of its founding director, Martha Twitchell-Muse, developed this prize and has supported it now for its ninth session. We're very privileged to be able to be part of this meeting to have Matt England give the presentation, and I'll leave that in a moment to Peter Barrett. But what I'd also like to add this afternoon is a small mention of something that's deeply important to SCAR. So SCAR is really a body of the International Council for Science which facilitates science and provides policy advice to the Antarctic Treaty System and to the subsidiary bodies of the United Nations. Importantly, though, today marks our 60th birthday. So we've been doing this for longer than the Antarctic Treaty has been in existence. And science has, in fact, changed policy both in the Antarctic and more broadly over that full period. And I think now, and all of you at this meeting will recognize, that sort of influence and the kinds of science that you do and we'll hear about this afternoon has become increasingly important. We'll celebrate our birthday with a little cake this afternoon at tea, so I'm inviting you all to that, of course. But without further ado then, I'd like to hand over to Peter to introduce our lecturer for this afternoon and the prize. Thank you, Peter.
Yes, thank you, Stephen. My name is Peter Barrett, and I'm the chair of the Martha Muse Selection Committee. I'm also a geologist, so when I gaze at the oceanographers and climatologists out there, I realise that I've actually come to know you over many years because I sailed over your ocean and I experienced the Antarctic and got an interest in climate that way. I did not know when I first went there in 1962 that it was going to melt. So I'm delighted to be here in this capacity to award the 2017 prize to Professor Matthew England. And it's actually a privilege to attend the meeting. I've chosen to stay for the whole meeting and listen to the latest on changes in Earth's climate and future prospects from a Southern Hemisphere perspective. I come from New Zealand. So briefly, what is the Tinker-Muse Prize for Science and Policy? It's a $100,000 US award. It's presented to an individual in the fields of Antarctic science and policy who has demonstrated potential for significant and sustained contributions that will enhance the understanding and preservation of Antarctica. As Stephen has mentioned, the prize is named for Martha Twitchell-Muse, an American businesswoman and philanthropist who worked mainly in South America but had a passionate concern for Antarctica. But it's also particularly a legacy of the International Polar Year, and it was really established through the foresight of the United States National Academy of Sciences and the Tinker Foundation, who I guess had a sense that it was good to have her passion linked with the concern for the preservation of the Antarctic region. The prize is deliberately targeted as a mid-career award, upper age limit of 50, on the date that nominations close this year, March the 14th, so you have another month to submit a nomination. Each year we have, this is the selection committee has, to choose from 10 or so nominations, assessing achievement and potential in research, leadership qualities, communication skills, international perspective. So we're very grateful, not only to the nominees, but their nominators and those who write letters of support, because it's quite a significant effort. But back to Matt. You've been a remarkable achiever, in this critical area of Antarctic science and policy right now. And it's really our appreciation for the role of the oceans and the melting of Antarctic ice at the margins that has come to be so important. But it's not just that, it's your work in ocean modelling for the last 2 decades, checked by modern historical and paleo records, has been critical for improving the robustness of the models for future projections, and this work continues and is really part of this meeting. It also requires working with many diverse groups, including geologists, and communicating these results effectively to policymakers and the public, and at the same time keeping a sense of humour. I know all of you here face the same challenge, but I think there's a special thanks to those of you who spend time helping policymakers understand why the climate problem is real and urgent. But Matt has been doing this exceptionally well, so it gives me great pleasure on behalf of the Tinker-Muse Prize Committee and the Tinker Foundation to present you with this award. We hope this will make greater things possible for you and your colleagues.
Okay, thank you. Thank you so much, Peter and Stephen. I'll get to more thanks in a minute, but I'm just going to try to do something quickly before I erode too much time, and that is to set up myself better here. Just give me 1 minute. Okay, that was really time efficient. That was probably 20 seconds and it saved several minutes during the talk. That's good. Thank you so much for those kind words, Peter, and Stephen. Thank you so much for the introduction from the SCAR perspective and for both of you to travel here today. I'm going to get to some science, and I risk losing a fair bit of time on science because you don't get awards like this very often at all. They're once in a career sort of events. And so I'm going to thank a lot of people, and it might take about 10 minutes. This is not going to be like the Academy Awards, I hope, where you start clapping and I get pushed off the stage, because there's a fair few people to thank. I want to start off by acknowledging both the Tinker Foundation and the vision of Martha Muse for preserving Antarctica, for setting up this award. And it's an honour to join the 8 previous winners, including Stephen, to be Tinker-Muse Fellows and to advance Antarctic science and to advance the the consciousness of Antarctica in the minds of policymakers worldwide, because it is melting, and I'll get to that a bit later on. And also I want to acknowledge the efforts of SCAR in administering the award. Research can't happen without some funding, and I've got to thank the Australian Research Council that has provided me with my lion's share of external funds. And of course you can't get external funds and have them sit, they need to sit somewhere, and they've been, largely my career has been spent at this university, so I want to acknowledge the University of New South Wales, all my friends, colleagues, collaborators in the Climate Change Research Centre for providing such an amazing research environment for me to work in. I also want to acknowledge the national centres that we've had set up over the last couple of decades. Andy Pittman's the director of these centres, and We had one that's winding up this year, that Christian Jacob's running, and then we're moving into the next phase around climate extremes coming up. This is a national centre connecting so many of you here. You're all being thanked at the moment for your collegiate collaborations, for working across the field in such an important topic. And I want to also acknowledge my national and international collaborators. It's a lot of fun to work with you. I know there's probably 20 or 30 in the room. We come across a problem, it seems interesting, we pursue it because we're scientifically interested in it. Sometimes we find results that alarm us, but it's always exciting to be in this field of science. It's a real privilege to work with you. And I want to thank this bunch of people. There's so many photos there, and actually I've left off about 20. These are PhD students, former PhD students, postdocs, group members that I've had the privilege of working with over the last 20 or so years. I think I couldn't find about 20 photos, so I'm apologising to those who didn't make the cut there. And I want to start going back a bit in time if I can, because it's all very well talking about the present and how things are going now, but I want to actually acknowledge some mentors I've had, and this is not an exclusive list. I'm missing many people here because you get advice all the time as a scientist, and it's often really good advice from colleagues and collaborators who've gone before you. And these 5 fine gentlemen are amongst my most special mentors because they've played a huge role. Matt Tomczak and Stuart Godfrey as my PhD advisors originally, sending me down in a tiny research vessel called the RV Franklin, right down into the stormiest of conditions in the Southern Ocean. The wonderful Gary Myers, who passed away just over a year ago, who was my honours advisor, who taught me all about tropical oceanography. Trevor McDougall, ever since I met him as a 22-year-old or so at CSIRO Marine Labs, has kept me thinking about ocean mixing and the real physics of the ocean down to scales that most of the other individuals, except for perhaps Jason Middleton on that screen, don't think about as much as Trevor does. So thank you, Trevor. Glad to call you a UNSW colleague these days. And I want to also acknowledge Jason Middleton. When I first got to this university a number of years ago, that I won't say because it sounds like it's too long ago, but for about the first decade, Jason was really pivotal in helping me come from a research organisation like CSIRO, where I'd been before, and navigating the field as an academic staff member, how to find funding through the ARC, how to take on that role that I think is a real privilege. Any academic staff member at a university knows the fun it is to see the PhD students come through the groups, go on into careers themselves, and it really takes a bit of learning how to do that well. And I thank Jason for his time on that years ago. And I'm going back in time. Please indulge me just a few more minutes. These guys on the screen, they were really pivotal, not in 1969, we're not going back that far, but they certainly ran the models back in 1969. I had a Fulbright scholarship to go to GFDL in 1990, and hanging out in particular with these 3 fine people was wonderful there. Suki Manabe and Kirk Bryan pioneered climate modelling. Robbie Togweiler just thought so outside the box. It was just fun to interact with him. And that was a really seminal part of my career development to go to GFDL in 1990. And now I'm going back even further in time. What did I do before then? I was actually a mathematician over at Sydney University and educated by a bunch of great mathematicians over there. But all the while, when I was there learning about equations, I had this in the back of my mind. I was a very keen ocean swimmer and surfer. You can see there's a label there about the pressure gradient term. Pressure term, fluid flows in the direction of largest change in pressure. There must be no better example of a pressure gradient than this huge wave here. I've never been in a wave that size. Maybe the wave, you can see there's almost a secondary wave that's smaller, maybe that size. But anyway, I loved mathematics, but I didn't quite want to be a mathematician. So it was a wonderful discovery to find out there was a field of research that pulled together my love of the ocean with physical oceanography, with mathematics and physics and so on. And so where did that come from? Where did my love of the ocean come from? That's why I'm going to quickly acknowledge these fine people here. My mum and dad are here. They haven't actually seen me give a talk, I think, for a long, long time. I think it was one that I gave when I was about 20, but it's been a while. Welcome back. I think they're responsible for my love of the oceans. We used to do these trips down to the beach every single day we could on a Sunday. In the Valiant, boards be thrown in, surf mats, whatever would float on an ocean wave. And this is part of my childhood. And so I sort of grew up loving the ocean, wanting to understand it. I once got lost, apparently, at the beach, off in a rock pool, looking at the starfish or whatever. But Mum was terrified she'd lost a kid. But anyway, I'm sure this gave me a love of the ocean, and to this day, I really can't function without getting in there first thing in the morning. So thank you for letting me go through that. I actually got some crazy footage here of my first time at the ocean, but let's not go there. I think I've given many thanks. It could go on for a lot longer, but I shouldn't do that because, of course, we're here for some science as well. So thank you to everybody that I've just acknowledged. Thanks to the Tinker-Muse Foundation and SCARA and so on. I should quickly mention the family that I referred to, I didn't quite finish. My apologies. There's a whole bunch of them. They're not just my mum and dad. There's my wife, Katie, 3 kids, brothers, sisters, uncles, aunts, nieces, nephews. They're a great mob. It's been a privilege and a pleasure. Okay, why is it important to acknowledge my kin? Well, sometimes we go into battles. You wake up one morning and you see something like this. This is the front page of the Australian newspaper, just when FIFA was being implicated in all sorts of corruption. And they're likening the IPCC is to science what FIFA is to soccer. And, you know, at the time I was at a wonderful meeting that Jerry Mill was running in Aspen, and I get all sorts of messages late that night there because, of course, it's morning time here. And so when these things come along, it does take some recovery. These kicks in the guts as a scientific community, these times where we have our science, you know, pilloried the way it is across media agencies, politicians and so on, it does take its toll, and you need a very supportive family behind you, I think, and wonderful colleagues and friends, great students to work with. You need a team of people around you to help you get through this. And I think as a community, we've shown resilience, but it's been a tough fight to get there. Okay, I might skip over showing some of the worst examples of that sort of behaviour. All right, thank you for indulging me those sort of 7 or 8 minutes, way past the Academy Awards usual limit of a couple. I've got about 25 minutes now. And so what I want to talk about is just 2 ways. I spoke about Southern Ocean water mass changes for the last 4 decades. And in the time I've got available, I'm going to touch on mainly 2 of these water masses shown in this diagram. One is the surface waters. I'm going to talk about surface trends over the last couple of decades. I'm also going to get into this panel here on the right-hand side, the trends in Antarctic shelf water right up against the ice shelves and ice sheets. I should acknowledge that's a tiny, tiny volume of Antarctic water that I've captured in this talk. This is a lovely schematic that Adele Morrison put together showing all of the interleaving of water masses in the Southern Ocean. They all matter, and they all matter a lot. And many of them are changing over timescales that we didn't think would be possible for these water masses. Bottom water's warming way faster than we thought it could. Mode and intermediate waters are closer to the surface. They're changing as well, but maybe that's to be expected because they're ventilated so quickly. But I'm going to stick mainly to the shelf waters against Antarctica and the surface trends, because the surface trends obviously are what we're subducting into the ocean interior. So here's a quick synopsis of the trends in the Southern Ocean surface, and so largely on the atmosphere. Dave Thompson's probably somewhere in the audience. He really pioneered some of this work, and Dave Crowley and others. But in the top right panel, you can see trends in geopotential height in Dave's 2002 paper. That's like a proxy for sea level, if you like. Down the bottom, there's wind stress trends in air temperature, and then alongside are ice trends and SST trends, trends in surface temperature. The short story is that the mid-latitude jet is contracting poleward. In response to that, there's been a whole bunch of other changes as well. Rainfall has increased over the southern extent of the Southern Ocean. As a result, salinity's diluted into less saline values. Ice has changed in a complex way. I'll get back to that in a second. Air temperatures have changed in certain ways and so on. So it's a complex story, but we do know that the southern hemisphere atmosphere has changed remarkably. Largely, this southern annular mode shift poleward. And a lot of you have seen me show diagrams like this. This was put together by Alex Sengupta originally when he was a grad student, and Dave Thompson and I and others used it in a follow-up paper, but it shows you a cross-section, depth in the ocean, altitude into the atmosphere, and northwards is going across to the right. It shows you a schematic of what happens to the climate system when the southern annular mode goes into this positive phase, when these winds shift poleward, the cloud cover, the storm tracks shift poleward. That changes air-sea heat fluxes in a certain way. The ocean gets cooler to the south and warmer to the north. Eddies actually tend to accelerate, spin up. Andy Hogg had a lovely paper on this a couple of years ago. And the whole of the ocean is responding, and some of it matters a lot because, for example, carbon depends on surface temperatures, changes in ecosystem are occurring, and so on. And ice is melting, and I'm going to get back to that a little bit later on. Okay, I spoke about salinity trends. This is measurements from Paul Dirac and Sue Wiffles, showing this broad-scale freshening of the Southern Ocean, and that matters actually for temperature. I'll show you some work on that in a second. And so one of the big things that came out of the Antarctic, one of the big challenges for oceanographers in this field of looking at the property changes in the Southern Ocean was this cooling trend and ice expansion over Antarctica. Excuse me. And so what's happened is, basically, I should show you a plot of this sea surface temperature again for a second. Looking at this lower two panels, this is from work by Ariane Purik, who I just glanced in the audience, I think. Ariane, in her PhD, has looked at these surface trends, and it shows on the middle panel there this quite remarkable cooling of the far Southern Ocean. This is in stark contrast to the Arctic. The Arctic, as you all know, has lost a huge amount of ice over the last couple of decades, and yet it's also sitting on the polar cap. So why is there this big difference? Clearly the geometry is very different, with Antarctica as a landmass sitting on the South Pole, whereas in the Northern Hemisphere, the Arctic is an ocean itself. So why is there this cooling? It was a big challenge to the community. When it first came along, there were the doubters saying, this sort of shows that climate change is not going to be as pervasive. They weren't necessarily saying it was wrong, but Antarctica is safe because sea ice is expanding and SST, the sea surface temperature, is cooling. And we now know a lot about that trend in surface temperature. One piece of research that came out likened that trend. This work by the MIT group suggested that trend was largely wind-driven, Ekman transport to the north, delaying warming, and that eventually you'd get this upwelling of circumpolar deep water, the warmer stuff that then would melt back the ice and so on. So it's almost like a delayed response to climate change, cooling for a few decades and then warming. And there's a lot of validity to this argument. I think there's a lot of evidence that this is played out. But there must be more than that, because all of the models that we look at for climate projections, if you average them, they do get the wind trend on average. Some get it more than others, but on average they get this wind trend poleward. But they don't all get a cooling. In fact, most of them get a warming. And this again posed a real challenge to the Antarctic climate modeling community. What are we getting wrong? And so the top panel again is the observations of SST trends and ice trends, and the bottom panels are the multi-model averages of ice and sea surface temperature, which look very different to the observations. And so a lot of work had to go into this. It's been about 5 or 6 years worth of research across many agencies. And one of the things that struck me when we did this work, and among many, a lot of other people were involved in this, is that we really only have one Earth to observe. But we have actually the capacity to model hundreds of Earths. And anybody involved in the CMIP5 project and CMIP6, Jerry Meals here, I know, and somebody like Jerry has just put his career into this process of making sure, and many others have been involved in this process, of making sure we get the CMIP process as good as we can get it. It's a wonderful initiative. It involves all of the major climate labs around the world, generating these simulations that are enormous amounts of person power. Tens and tens of people years go into building even just one small parameterization or one small component of these models. So accolades to everybody involved in CMIP5 and coming up CMIP6, because we get these simulations here. All these tiny little pixelated images of Antarctica are from different climate models. And if you stare at those long enough, you can see when Ariane produced this, we agreed the best way to show it was not by alphabetical order at all, but to show them from the cooling most model to the warming most model. And I think this is configured this way. And you do have some models that have a cooling trend over Antarctica for the last 30 or 40 years. Most warm. So what is it about the models that cool? That's one thing you can do. And Jerry had a wonderful study out a couple of years, but 2014 and 2016, that put part of this piece of the puzzle together. He showed that if you subsample the models that got this early 20th century slowdown in surface temperature, those models that got that tendency for the interdecadal Pacific Oscillation to be in the right sign, because that's a natural mode of variability. They did this sort of by chance, if you like. when they did, if you look at the average of those models, you get this pattern of ice expansion. It's very hard to see here, especially if I use an arrow on my screen, you can't see it at all, but this panel here shows that when you subsample those CMIP5 models that had the so-called slowdown, they also see this ice expansion. So that gave us a big hint that actually natural variability is part of the role of this ice expansion. It's just a decadal mode of variability in the system, and it's not going to be around for long. We know the IPO is likely changing into a positive phase. That would be into a positive phase that would be characterized by less ice around Antarctica. Certainly in this Ross Sea sector, the cooling that's been seen there is likely to diminish. Now, causation, really you want to go into models and actually force them to have a certain pattern to examine if they are. You know, if your sense that something's linked needs testing, you go into a climate model and you change the model in a way that tests that theory. And these pacemaker runs that Kosaka and Shi made famous a couple of years ago and that many people are pursuing around the world are really wonderful examples of how you can test the climate physics that we're observing on our planet. The one observation system we have against models is to go in there and change the models in a certain way. And if you go into these models and impose this sea surface temperature trend in the Pacific Ocean, you find out that part of the reason for the linkage that Jerry found between the slowdown models and this ice expansion in the Ross Sea is due to this link from the tropical Pacific, due to this link to the IPO as he hypothesized. Because if you can go into those models and impose the SST fields there, as you see in this top panel, you get the sea ice trends dropping out. This is a paper that Ariane and several of us got published the year before last in Journal of Climate. Okay. I want to get on to a couple more topics before my time's up. And one is to come back to this freshening. I mentioned the way if we shift the storm tracks poleward, you do get more rainfall over the higher latitudes of the Southern Ocean. And by getting more rainfall there, you see the salinity decrease. And that salinity change is actually enough to be part of the reason for this cooling and ice expansion. And so again, I'll just walk you through these diagrams here. This is the Dirac and Whiffles trends in sea surface salinity. Apologies, the pointer's a little bit faint, the top panel. The lower panel shows the simulations in the CMIP5 runs in the grey shaded lines, the faint lines. We don't say which model's which, doesn't really matter for the moment. And the dashed line is the zonal average of this plot here. And if you look at that diagram, you can see that some of the models are indeed getting the freshening that has been observed, but many of them don't. And some of them get a salinification. And on average, they certainly get a weaker freshening than's been estimated from the observations. And so what we did in this experiment, it's a slightly different pacemaker experiment. We shouldn't call it a pacemaker because we don't propose that the Southern Ocean sea surface salinity is a pacemaker for global climate, but we do think it's a pacemaker potentially for this local cooling. And so we ran a model where we actually force those models to have the salinity trend like has been observed. So we're just making sure that the freshening that was observed by Dirac and Whiffles gets into those climate models, because we want to see, how does that matter? Does it matter that they're not getting this freshening on average, or they're not quite getting the magnitude of freshening that's been observed? And it does matter. If you look at the observed, this is a remarkable diagram to me, because there's nothing in these climate models. This is again work by Ariane Purek, who's graduating this year. She's done such wonderful work around this Antarctic space. I keep showing your work at talks I go to. But this is observed versus simulated, and the only thing that's changed in this set of models is just this freshening being imposed at the surface. No mechanical wind forcing whatsoever. There might be a tiny wind feedback, but it's small. You know, changing sea surface salinity doesn't do much, doesn't at all to the local wind fields. If you change something in the tropics, that might impact. But on the left-hand side of the observations, on the right-hand side is the coupled climate model, and the trends if you impose the Dirac and Whiffles freshening. So just that freshening alone is enough to account for the cooling. So I think part of the story is the variability of the IPO that we've seen over the last couple of decades. How that's played out has given us the ice trends that we've seen. But the other part of the story is this freshening, this stabilization of the water column. Back to my schematic, mixed layers become shallower when you freshen them. If you've got a shallower mixed layer, wintertime cooling over the Southern Ocean is that much more effective at making for cooler temperatures. Just, you know, basic heat budget, processes. Shallow mixed layer sees more cooling of the surface mixed layer. Okay, I'm going to finish up now with my remaining 10 minutes to allow 3 minutes for question. I rarely finish talks on time, so I hope I can get there. But this last bit is going to be, I think, the most important in terms of where Antarctica's future is headed, because this is about the ocean warming on the shelf right up against Antarctica. And it's these red patches that we're particularly concerned about. But we're also concerned about the stippled areas. If you can see, there's a lot of stippling there. And those regions are regions where we have really no idea what the warming rate's been. There haven't been enough measurements to make that estimate. These trends are from Schmidt-Co et al. A couple of years back. A lot of work is going on globally to understand these trends, to understand where those trends are going, because a whole lot of ice depends on it. Peter gave the nice statement, but also an alarming statement. In 1962, he didn't expect it would start to melt like it is melting. These red dots refer to the size of the magnitude of the melt, and the blue dots the magnitude of growth, and the size of the dots correspond to how much melt or how much growth there is around the ice shelf. So these are the floating bits of the ice, the extensions of the ice sheets that float in the ocean, and they're obviously subjected to ocean melting from below, and they're also subjected to atmospheric warming from above. So you can melt ice in many ways. This beautiful photograph of a pond, of a sort of ice shelf lake that forms, you could imagine looking at that. The whiteness of the ice is very reflective, so heat's reflected. The blueness of the lake, as beautiful as it looks, it actually absorbs more heat by being that color. And so you get a feedback effect there where you can eventually get the top panel here. These remarkable photos that appeared on the cover of Science a couple of years back, these moulins, which are basically percolated holes like Swiss cheese, where the warmer water that's originally sitting on this pond here melts its way through the ice. And these can go many hundreds of meters. I don't know what the thickest measured has ever been, but I believe it's of the order of, through an ice, a big, thick ice shelf or ice sheet. This is up on the Greenland ice sheet, this top panel here. You can see the scientists. I wouldn't be standing just right there. I mean, for the photo maybe for a second, but it looks like a scary cascade of water down there. So you can melt the ice shelves and ice sheets from above, clearly from atmospheric warming, but the warming from below is particularly profound because the heat capacity of seawater is so much greater than the heat capacity of air. We'd way sooner have 1 degree C of warming over we don't want warming either in the ocean or the air, but we'd rather have it in the atmosphere because there's just not the same heat capacity as the ocean. The ocean stores heat incredibly effectively. It can transport that heat somewhere else before it's then released to the atmosphere or allowed, in this case, to melt ice. And so in this case, you've got this schematic diagram showing some of the sub-ice shelf melt, some of the processes at play, just a real simple cartoon. But clearly, one of the big questions for oceanography at the moment is how fast is this water melt moving onto the shelf? Where's it come from? What are its properties? When it gets into the shelf, the ice shelf cavities, what does it do there? How does it melt the ice? What sort of feedbacks are at play? And there's a growing field of research here. I found this diagram intimidating in Rob de Conto's paper a couple of years ago. Rob showed the Antarctic continental image that I'm used to seeing. This is not the confronting one. This is just the one that you're probably all used to looking at. If it was all white, you go, there's Antarctica. You recognize it. It's got ice speed shown there in color shade. So you see the major ice shelves flowing in the Weddell sector and the Ross sector. But the diagram that really confronted me was just below. And this is Antarctica, where Rob and Dave, they color shaded the map so that where it's green, it's above. It's not tropical forest at all, although in past climates, apparently there were alligators roaming the Antarctic, but when the ice was all gone, it was warm enough. But the green is above sea level, and any shade of blue or grey is below sea level. And you can see all of a sudden, Antarctica is not like a massive continent with bedrock well above sea level. A vast majority of what you see from space as the ice sheet is actually sitting what looks to be precariously on some of these islands. If you look over the West Antarctic region, the vast majority of the ice area there is sitting over bedrock that is well below sea level. And so the great concern amongst scientists now is how do we reconcile these processes that we know are happening on the shelf with the fact that there's about 50 metres of sea level locked up in the ice. We don't think that all of that 50 metres at all is unstable to anthropogenic emissions of greenhouse gases, but Rob's work a couple of years ago modelling these ice sheets show that from Antarctica alone, many metres, up to 15 metres by the year 2500, can be carved into the ocean to raise sea levels by levels that would obviously hugely disrupt all of the major coastal cities of the world. There'd be hundreds of years to get to this adaptation, but nobody would deny the cost of that adaptation would be absolutely enormous. So here's the warming signature. So as an oceanographer, we get excited about this signal we're trying to understand. This warming signature is a hard thing to understand, so we put aside the environmental ramifications for a moment. And Paul Spence, one of the wonderful guys I've worked with over the years, one of the postdocs, he's now a DECRA fellow at the CCRC, ran some simulations where, I'm just going to skip a few slides because I want to get to Paul's work. Paul ran some simulations where because this is what you do when you've got a climate model or an ocean model, you can play games with it. And you do this not because you want to play games with the model, it's just that you learn more and more by doing the sorts of things that Paul does, which is to say, grab the model. In this case, he'd looked previously at how wind shifts around Antarctica he'd written a paper in GRL that myself, Andy Hogg, Steve Griffiths and others were involved with, looking at the changes of warming around the West Antarctica, just basically wind-driven circulation. This schematic diagram on the lower left here, very simple Ekman-driven dynamics. It seemed to play out and account for the warming we got in simulations over the last 50 years. So we got this warming signature was retrieved in the model, and we got that with just simple wind forcing of a wind trend in the simulation. Basic Ekman pumping dynamics, and we're not saying that's not playing out at all, but it turned out the story was way more complicated than that. And Paul discovered this kind of serendipitously by going to the model and just actually applying the wind stress in this sector here, the red shaded region. He just applied the wind stress only in that sector to see if there was any remote teleconnection of that wind anomaly around Antarctica, because he knew that Kelvin waves can be trapped by the coast and they propagate around Antarctica very effectively. I might show you just an animation of one of these so you know what I mean. Here we go. These waves, this is a PhD project by Dave Webb, who's now working on the exact processes and how much this can change the thermal structure on the shelf. These waves propagate very effectively around Antarctica. Tide gauges show you that they are there all the time. Some of their energy propagates up into the North Atlantic, but they're ubiquitous in Antarctica. Here are some measurements of them. There's some measurements of them. I'm going to have to finish up quickly because I'm almost out of time. So we know they're there, and if they're there, what are they doing? And so the wonderful thing about Paul's model is that applying this wind stress anomaly around Antarctica led to a warming signature very rapidly appearing on the West Antarctic region. And so there had to be a reason for this that could get that signal there. It was really quick too. It was the anomaly first appeared within weeks to months. Nothing can propagate an anomaly that fast except a sort of planetary scale wave. And so the work that we're doing at the moment is really trying to tease apart this process. This is a schematic that Dave Webb put together with Ryan Holmes, myself, and Paul and others. This shows the anomalies in a cross-section under the shelf. These coastal trap waves are what we call barotropic, which means they're top to bottom. It means they actually change the circulation right down to the bottom. And when they do that, these sort of arrowheads coming out of the page, when they do that, they actually lead to a bottom boundary layer response in the Ekman layer. All of the boundary layer meteorologists or oceanographers know about Ekman layers in their work, but you also get bottom boundary Ekman layers in the ocean. And the way these Kelvin waves work is that creates a flow onto the shelf. And actually the coastal oceanographers, Peter Oak, told me about this mechanism 20 years ago, and I forgot about it, and then it's come up again around Antarctica. But it shows how these coastal trap Kelvin waves can generate on-shelf flow, and so we're currently exploring exactly how big that process can be. The one thing I would say that alarms us is that if you look at the energy of these, this bottom panel shows the, if you like, the velocity anomaly of these barotropic waves. And where it's intensely red there shows that the speed is fast. And so we expect this mechanism to be strongest where you have a rapid barotropic velocity from these Kelvin waves. And you can see the most exposed part of the Antarctic continent, bearing in mind, I should say, that the reason this is all red here is this is where the wind anomalies are. Okay, so that's where we're generating the anomaly. You don't see significant anomalies up on the shelf until you get to the West Antarctic region. So this alone, the geometry of Antarctica is creating the conditions ripe for this melting. It's a little bit of a complicated point to end on, but the bathymetry lines, you can see the wet LC, Polinia, all the oceanographers and atmospheric scientists join me here. Look at this, the bathymetry gradients here are very weak. Around here, the bathymetry lines converge very rapidly. So the planetary vorticities, conservation of planetary vorticity means these barotropic Kelvin waves really accelerate over the Antarctic region in the West Antarctic sector. And we think this is part of the reason why that bit of Antarctica is particularly vulnerable, apart from the geometry of the islands and so on that I showed in the previous diagram. All right, it's time to wrap up. So I'm going to actually finish up with just a few more general graphics that are really for people in the audience who maybe aren't even in the field of ocean atmospheric research. Just 2 more minutes on this. The one thing I would say, whilst it's wonderful to make these modelling studies, we always need to come back to the observations, and at the moment Antarctica is badly undersampled, both over the continent and under the shelves. We have so few measurements of the region. These programs, SCAR and so on, support SEUS, the Southern Ocean Observing System, CLIVAR, WCRP, all these agencies are trying to push for these measurement programs to go ahead. We need more of them. Satellites don't really work for altimetry really close to the continent. The Argo floats have had challenges up under the ice. So the observations really are primary for understanding the system. The models do help us understand what the observations bring back, but they don't in themselves observe the system. You really clearly need measurements for that. But projecting to the future, there's only 2 ways we can do that. One is looking back into the past, and we already know from past paleoclimate records that when warming goes up, sea level goes up, and we have estimates of ice melt around Antarctica that show how the ice responds there. And the other way is obviously through these projections, and I'm just going to finish up with Rob's projections. I mentioned them all earlier. If I say 5 to 15 for the high-end scenario, Rob comes up with about 15 metres of global sea level rise if we do nothing. This is this RCP 8.5 scenario. If we do lots, if we meet the Paris Agreement, we're right down at keeping Antarctica as a frozen continent, as we'd like it to be, not just because of the lovely continent it is by being frozen, but because also it's holding sea level intact for us. We need it to be stable for the world's cities to have stable levels of sea level. The last slide, only 2 of these are photoshopped. It's confronting to think that. You can see which ones they are quite quickly, but I'm going to just thank you for your time. Thanks.
Thanks, Matt, that's wonderful. And especially the last slide, second to last slide, just reminding us that this is a critical time, but that we have a choice. And that's for the politicians to make, but it's the work of you and these people here that's actually giving the information of the choice. But perhaps there's other questions out there. There must be 1 or 2 before the next session begins. We'll both be around for the whole conference. You're welcome to check with us. I think,
One question out there somewhere. Either it was really clear what I said or it wasn't that good. Thanks for your attention anyway. Thank you.
Yes, thank you all.
There's one question.
Sorry, I've just been given the mic. The one question. So the Kelvin waves that are generated in that you meant, are they generated by the synoptic weather patterns? So they have the synoptic frequencies. Is that
Exactly. I recognise Peter Baines. I can't see where you are.
I'm right here.
My former boss from CSIRO. Peter, good to see you. Yeah, there's generated by synoptic systems, and so, but when you get a inverted commas permanent wind change, so applying as the southern end shifts poleward, that wind change is stationary, and so whilst the anomaly propagates as Kelvin waves, it actually progressively builds up an anomaly over time. And so you're right, initially it's just these bursts of barotropic waves. If you look at the temperature signature we get in the model, you can see these barotropic waves pulsing past via the synoptic systems, as you say, but over time with a long-term trend, you do get a sea level anomaly that leads to a stationary, if you like, barotropic velocity anomaly that generates those bottom Ekman layers.
Thank you.
Thank you, Peter.